Welcome to data management in looking at graphing concerns with correlations with both linear and nonlinear data sets. Correlation is such a strong tool to be able to use, finding the relationship between any two sets of data, but there are limits to it. And a correlation value, your R value, can also be used to manipulate how you describe a data set to show that it's a stronger strength than it is. And then there's also situations where the R value just fails. And that's really what this spreadsheet looks at. This is a brilliantly designed data set that you will hopefully recognize what's happened here as you start to calculate R values. But you have four fairly simple data sets. No variables are given to you. We're just going with an XY variable, which is all we need to be able to create a scatter plot and find a correlation value. But as you find the R value for each of these four data sets, you'll quickly start to recognize a pattern that's there. And then when you graph it, you'll see different issues that are going on. So really the focus today is to, yes, get the R value, but to more so be critical of the R value and decide when it's valuable and when it's not. And then to also look at the situations where we have a nonlinear relationship. And what's tricky with a data set, and I'm going to use this one here as an example, is that when you first look at it, you don't always know if it's going to be a better linear or nonlinear relationship. And so I'm going to start by just doing the test that we always have to do, which is looking at what the linear correlation is. So my linear correlation, R is equal to, I'll use the formula that is probably used the most in statistics, correl for my first variable of data, and then highlighting my second variable of data, and I get an R value of 0.81. I need to go and decrease the decimals down to the standard 2 decimals that correlation is always rounded to. And now from that, I can go and conclude that I have a strong linear, strong positive linear correlation. And that is often where we would end. We would graph it, we'd see that linear correlation, and then go from there. So now to graph, I'm going to do the standard process where I highlight both columns of data that I want to graph. We'll go to insert, look at the different either recommended charts, we can just go directly to the scatter plot. And the first thing that should jump out to you here is that we do not have a linear relationship. So I'm just going to go with this default one. Usually we would spend some time to go and ideally format this, start adding our titles, etc. For this little exercise we're doing today, it actually works best if you just go with the standard square shape. And we always want a square shape for our scatter plots so that they're easy to compare and so that we don't accidentally change the strength or the look of the strength of the correlation. So rectangle here takes away that parabola shape that was already evident. Where you have that square shape, you see the relationship in the way it should be. So I'm going to skip the step of adding axis labels and all those other components, because really what we want to investigate here is why this is not a linear relationship. If I was to put a standard line of best fit onto this, it does look like a strong relationship, but clearly strong positive linear correlation is not the best option here. I'm going to click on the graph and go to the little plus symbol. And then rather than just default hitting the trend line and getting that linear line that we usually would, I'm now going to go down to more options. And Excel gives you a huge range of possibilities to be able to look at different relationships. And when it comes to dealing with a nonlinear case, there's no formula here or one true way. It's not like equal to correl where there's a nonlinear version of that. And that's because there's no one nonlinear curve. We could have exponential, we could have specific doubling, tripling curves, we could have the power, the regression, the polynomial, logarithmic, trigonometric, circles. There's so many nonlinear relationships that we have. That really the best way is just to start going through them and to say, does this look like the exponential curve? We already know the linear is a strong positive, but I want better than that because I know that line, that straight linear line of R is equal to 0.82 is not the best representation for this data. Logarithmic, it's getting closer. And then when we hit the polynomial, right away we can go and see that that follows the line. And here we really have that parabola shape. And so then the next step that we need to do, we would always display the equation on the chart anyhow, but now we're going to go another step, and I'm going to move it down here just temporarily so that it's off of the grid. We would always add the equation, but I'm now hitting that R squared button as well to go and show that there is actually more than a strong correlation. There's a perfect correlation at this point. So I have a perfect nonlinear correlation, which I get from the R squared is equal to 1, and then we know it's a parabola. There's lots of things that need to get changed on this format-wise, but the first thing immediately is that we have way too many decimals being shown here, and so I'm going to go over to an example that's a little bit closer to completion, and for comparison's sake, with the 4 different data sets you have, this is enough work to do. We don't need to add on all the extra axis components, axis labels, titles, etc. What I have here is an equation where my values have been rounded. I just went to 2 decimal places. 1 decimal place would be fine too. That shows the x squared for the parabola. And then we have R squared is equal to 1 to go and show the perfect positive. So now look at the explanations. This still stays. My R value of a linear correlation is still 0.82. The perfect nonlinear parabolic correlation, though, is now the best description. The key word there being perfect because of R squared is equal to 1 and the fact that it's a nonlinear correlation. And if this was a classic tripling curve, I could say it was an exponential curve where the change rate is 3, so like 3, 9, 27, 81. But in this case, we're just going to say that it is a parabola. So the key here is that the R is equal to 0.82 value is wrong. This is not a linear relationship. This is a nonlinear relationship with R squared is equal to 1, which means the perfect nonlinear correlation. And if we go back to the data set, just from a quick glance at this, there's really nothing that to me immediately jumps out as being a nonlinear relationship. Until we go and change this, and I'm just going to do a couple little format changes here, or maybe we'll just leave it so that we have this value. But now if I go and sort by my x value, I can see that as my x value increases from 4 to 14, I have a 3.146. We have it increasing in a nonlinear fashion. There isn't a straight linear relationship that's here with the y values. And so that's it. I have my data table sorted. I did it in a way that kept the pairs of data together. So the 8 is still with the 8.14, the 14 is still with the 8.1. But then I have a graph that shows the nonlinear situation. So this is the process to follow for all 4 of the data sets that you have. You'll see that some are a little bit more traditional where you do have that linear relationship. There's no clear nonlinear one here. And as you work through the other ones, you'll be able to see the patterns that emerge. So that's the key. When you're done, go back and check the 4 steps that are here. I went and completed the R value. I described it. After that, I have a quick scatter plot. But now I'm doing that kind of experiment of also going through and seeing the different values that you get for the trend line options. And just a reminder that you can never have this. You cannot have a situation where you're putting both a linear and a nonlinear trend line curve onto it. We're only ever going to pick the best option. And the best option is always the one that gives you the strongest correlation. So that's it. That's the process that you're going to go through for each of the data sets that are here. I do recommend setting these up in a table where it can be sorted. It's purposely been done in this situation. It was purposely done to go and have a data set where your X values and Y values are scattered. And that's something that's not ideal. we want to immediately try to bring order in wherever we can. What's ideal is to go and set these up for sorting so that as the X value increases, we can see the change to the Y value. So complete this spreadsheet, go and compare it with the answers or when it is taken up in class, and hopefully this helps you be more critical of the default R value that you get. Just because of the strong correlation does not mean it's always the best option.